Introduction to Bayesian Statistics, Priors and Posteriors. Welcome to your first hands-on lesson in Bayesian statistics. We will explore what priors and posteriors mean, why Bayes' rule matters, and how to use Python to run simple Bayesian updates. By the end, you will build intuition for Bayesian thinking that is useful for science, medicine, and AI. Let us get started. Running the cell now. First, let us make sure Python will not show warning messages. Then we load our required packages for math and plotting graphs. This will make working with data easier and more fun. We are telling Python to hide warning messages so we can focus. We import NumPy to handle math operations and random numbers. Pandas is imported to work easily with tables and structured data. Matplotlib is brought in to create visual charts and graphs. Seaborn builds on Matplotlib to make prettier statistical plots. We set the random seed to 42 for reproducibility. We set a style to make charts have a clean white grid background. This style choice helps keep our plots clear and readable. Running the cell now. This code block sets up the environment by importing essential libraries and configuring plot aesthetics, which is why there's no visible output here. Notice how the random seed is fixed for reproducibility, an important step to ensure consistent results in Bayesian simulations. This preparation lays the groundwork for running and visualizing Bayesian updates in the lessons that follow. Now you are set up for data science work. Let us download a dataset and see how it works. Let us simulate flipping a fair coin 30 times. Each flip is either 1, heads, or 0, tails. We put the results in a table. Let us look at the outcome and count heads and tails. We are generating 30 coin flips using random numbers. Each flip has a 50% chance to land heads. We store all the flips in a pandas table. The printout shows the first 5 flips. Now you can see the actual numbers for these flips. Here is the summary of all the results. It counts how many heads and tails appear. Running the cell now. Here we see the initial dataset of 30 coin flips represented as zeros, tails, and ones, heads, with a nearly balanced count of 13 heads and 17 tails. This setup is key for the lesson because it provides the observed data we'll use to update our prior beliefs with Bayes' rule, illustrating how real data informs the posterior distribution. Notice the simple binary structure and total counts, which are essential for computing likelihoods in the upcoming Bayesian update. Practice, try simulating more or fewer flips to see what happens. What do you notice about the counts? What is a probability? Probability is how likely something is. For a coin flip, we say the chance is 0.5 or 50% for heads, and the same for tails. Probability in Python is often between 0 and 1. Let us start exploring these concepts using simple tools. Running the cell now. Now let us measure how common heads and tails are by finding their proportions. We are looking at the table to see how many times heads occur out of all flips. This gives us the estimated probability for heads. Tails is just what is left after removing heads from 100%. We print out both probabilities so you can compare. Now you have our coin's real observed probabilities. Running the cell now. This output shows the calculated probabilities of getting heads or tails based on the flips recorded in the data. Notice that heads came up about 43% of the time, which is close to, but not exactly, the expected 50% chance, illustrating that real outcomes can vary slightly from theoretical probability. This helps reinforce the idea that probability measures likelihood, not certainty. Think, if you flipped more coins, would your estimates get closer to 0.5? Why or why not? Introducing priors. What if you have some idea before seeing data? A prior is your belief about the chance before looking at new evidence. With a coin, maybe you believe it is a fair coin, or maybe you doubt that. In Bayesian statistics, we write down our prior as a distribution. Let us see it in action. Running the cell now. In Bayesian thinking, we choose a prior to describe what we believe about the coin before any flips. The beta distribution is a flexible way to do this for probabilities from 0 to 1. Here, beta 1 1 means we are saying any fairness is possible for our coin. We use the beta distribution because it fits probabilities between 0 and 1. Beta is often used as a prior for events like coin flips. X here is every possible probability between 0 and 1. Setting A and B to 1 each means all levels of fairness are equally likely. We find the prior's probability for each value of X. We make a simple plot to show the whole prior. This line shows all possible fairnesses at the start. The x-axis is chance of heads. The y-axis shows how much we believe each chance before data. The title explains that we are not choosing a favorite yet. We put a legend on the chart for clarity. Now the chart appears. You can see it is perfectly flat. Running the cell now. This plot shows the prior belief modeled by a beta 1 1 distribution, which is uniform, meaning we consider every probability of heads equally plausible before seeing any coin toss data. Notice the flat shape across all probabilities from 0 to 1, reflecting complete uncertainty or no preference. This connects directly to the lesson's goal of introducing how priors represent initial beliefs before evidence is observed. Try to change prior _A or prior _B and run again. What does it mean if the curve is not flat? What are likelihood and posterior? In Bayesian statistics, likelihood is how likely the data is, given each possible probability. Posterior is our new belief after seeing the data. The posterior combines the prior and the data using Bayes' rule. Next, we will update our belief about this coin, step by step. Running the cell now. Now let us do a Bayesian update. We add the counts of heads and tails from our flips to the prior parameters. This forms the posterior, our new belief about how fair the coin is after this data. We count how many times heads and tails appeared in our flips. We count the total number of heads from the flip column in our data. We count the total number of tails by subtracting heads from total flips. We update the first parameter of the beta prior by adding the number of heads. We update the second parameter of the beta prior by adding the number of tails. We calculate the beta probability density function for the updated posterior. We create a new figure with a specific size for plotting. We plot the prior distribution as a dashed line labeled with its parameters. We plot the posterior distribution as a solid line labeled with its updated parameters. We label the x-axis as the probability of flipping heads. We label the y-axis as the plausibility of each probability value. We add a legend to differentiate between prior and posterior lines. We set the plot title to explain that this shows our updated belief after data. We display the completed plot showing prior and posterior distributions. Running the cell now. This plot shows how the prior belief, a beta 1 1 distribution, is updated to the posterior beta distribution after observing the data, specifically, the counts of heads and tails. Notice how the posterior curve becomes more peaked around the observed proportion of heads, reflecting increased confidence. This illustrates the core Bayesian idea, combining prior knowledge with observed data to refine our belief about the coin's probability of landing heads. Notice how the shape moved. Try updating for a different number of flips or a different prior. Often we want a single estimate for our coin's fairness. One common way is to report the mode, the most likely value after updating. We use the formula for the mode of a beta distribution. This gives us the single most likely fairness based on all the data and our prior. If we do not have enough data, we just say it is 50%. Now you can see our best single guess for the coin's chance of heads. Running the cell now. This output shows the estimated fairness of the coin after updating our beliefs with observed data, reflected as the mode of the posterior distribution. Notice that the value 0.43 is slightly less than 0.5, indicating the data has shifted our belief toward the coin landing tails more often. This connects to the lesson by illustrating how the posterior combines prior and likelihood to give a new, data-informed probability estimate. Try more coin flips, or a different prior, then recalculate the mode each time. How does data change your belief? Priors are flexible. Try other examples. Some people may start with strong beliefs. For example, if you trust the coin heavily, use beta 10, 10. If you are very sure it is biased to heads, use beta 20, 5. Your choice of prior affects what happens, especially with little data. Let us see a new prior and how the update changes shape. Running the cell now. Let us start with stronger belief that the coin is about 50% heads. Beta 10, 10 is much more concentrated in the middle. We update as before and watch how the curve shifts. We start by defining a new prior distribution, beta 10, 10, which represents a stronger initial belief in a fair coin. Here we set the parameters A and B of the new beta prior to 10 and 10 respectively. We calculate the probability density function, PDF, of the new prior over X using these parameters. We update the posterior parameter A by adding the observed number of heads to the prior parameter A. Similarly, we update the posterior parameter B by adding the observed number of tails to the prior parameter B. We calculate the PDF of the posterior distribution using the updated parameters. We create a new figure with a specific size for plotting the distributions. We plot the prior PDF as a dashed line for visual comparison, labeling it clearly. We plot the posterior PDF as a solid line, showing how the belief updates after observing data. We label the x-axis to indicate it represents the probability of getting heads. We label the y-axis to indicate it represents the plausibility or density of those probabilities. We add a legend to help identify which line corresponds to the prior and which to the posterior. We give the plot a descriptive title summarizing the idea of using a stronger prior belief. Finally, we display the plot so we can visually inspect the effect of the new prior on the posterior. Running the cell now. This plot shows how starting with a stronger and more balanced belief about the coin's fairness, beta 10, 10, shapes the prior distribution into a sharper, narrower curve centered around 0.5. After observing the data, number of heads and tails, the posterior updates but still reflects this confident initial belief, illustrating how a strong prior influences the final inference less drastically than a weaker one. This reinforces the lesson that priors can be tailored to express different levels of initial certainty. Notice, stronger priors make the update move less when you get new data. Try experimenting with the numbers. Real-life example, Bayesian model in medicine. Suppose doctors want to estimate the chance a patient has a disease. They may start with a prior based on experience. Each new test result acts as data to update their belief. This is why Bayesian methods are so useful. They combine what you know and what you see. Running the cell now. Let us try updating beliefs using your own numbers. Enter how many heads and tails you saw, and also the prior you want. We will show the most likely fairness for your coin after updating. This is a comment prompting you to try entering your own coin flips and prior beliefs. Ask the user how many heads they observed and convert the input to an integer. Ask the user how many tails were observed and convert the input to an integer. Ask the user to input their prior parameter, for the beta distribution. Ask the user to input their prior parameter, b, for the beta distribution. Calculate the posterior parameter, by adding observed heads to the prior. Calculate the posterior parameter, b, by adding observed tails to the prior b. Compute the posterior mode, most likely fairness, using the updated parameters if sufficient data is available, otherwise default to 0.5. Print the estimated fairness of the coin with 3 decimal places based on your inputs. Running the cell now. This output shows the updated most likely fairness of the coin, posterior mode, as 0.667, based on the user's observed heads and tails combined with their chosen prior values. Notice how the calculation incorporates prior beliefs, user_A, user_B, with actual data, user_heads, user_tails, to refine the estimate. This illustrates how Bayesian updating helps doctors revise probabilities by blending experience, prior, and new evidence, data. Try different priors or counts and see how much the mode changes. Did your starting beliefs matter a lot? Bayesian inference and uncertainty. Unlike a single number, Bayesian inference gives us a full range of possible answers. We see how likely each possible fairness is after our update. Let us look at the spread, not just the most likely value. Running the cell now. A credible interval tells us what range the true answer is likely to fall in, given all evidence. Here, we show the middle 90% for the probability of heads. We use the beta distribution to find where 5% and 95% cut points are. These are the low and high ends of our credible interval. We make a new figure to plot these results. The line shows our posterior belief again. The 2 dashed lines show where our credible interval starts and ends. We label the cutoff points for clarity. Same x-axis as before, chance for heads. Our title explains we added a 90% credible interval. Legend shows which line is which. Layout keeps the legend visible. The plot shows the range is quite wide. We print out the interval numbers so you can use them. Running the cell now. This plot shows the posterior distribution of the coin's fairness, with the shaded region between the red and blue dashed lines highlighting the 90% credible interval. Notice the distribution is centered roughly around 0.44, reflecting updated uncertainty, not a single value, about the probability of heads after observing data. The printed interval, 0.30, 0.58, quantifies where the true fairness most likely lies, aligning with the lesson's goal of expressing uncertainty through Bayesian inference. See how the interval shrinks when you use more coin flips. Let us flip a new, slightly unfair coin 100 times and repeat the update. Watch how having more data makes our interval smaller and belief more precise. This time, we simulate 100 coin flips with a 60% true probability for heads. We count the number of heads that occurred in the simulation. We calculate the number of tails by subtracting heads from the total flips. We set the posterior parameter by adding 1 to the number of heads, reflecting the prior plus data. We set the posterior parameter b by adding 1 to the number of tails, reflecting the prior plus data. We calculate the 5% lower bound of the 90% credible interval using the beta distribution's percent point function. We calculate the 95% upper bound of the 90% credible interval similarly. We create a new figure for the plot with specified size. We plot the posterior distribution's probability density function as a green line. We draw a red dashed vertical line at the lower credible interval bound. We draw a blue dashed vertical line at the upper credible interval bound. We add a label to the x-axis indicating it represents the probability of heads. We add a title to the plot explaining what it shows. We add a legend to distinguish the plot elements. We adjust the plot layout for clarity and neatness. We display the plot on screen. We print the numerical credible interval with formatting for easier reading. Running the cell now. The plot shows the posterior distribution for the coin's fairness after 100 flips, with a 90% credible interval tightened to roughly 0.51, 0.67. This narrowing interval compared to fewer flips illustrates how more data reduces uncertainty in Bayesian inference, giving us a more precise estimate of the coin's true probability of landing heads. When you gather more evidence, you become more confident in your answer. Recap: priors, posteriors, and Bayesian thinking. Bayesian statistics lets us start with our own beliefs and update them as we see data. The key terms. Prior: what you believe before data. Likelihood: how likely you would see this data. Posterior: your new belief after combining both. Now you can apply Bayesian reasoning to coins, medicine, and science problems. Running the cell now. Here is a final challenge for you. Set the coin's real chance, number of flips, and prior belief. Then see how the results compare to what you expect. Practice challenge: change prior beliefs, sample size, or true coin probability and see effects. Enter the true probability of heads for the coin you want to simulate. Enter the number of times you want to flip the coin in the simulation. Enter the set parameter of your beta prior distribution. Enter the BA parameter of your beta prior distribution. Simulate flips as a list of zeros and ones representing tails and heads respectively. Count how many flips resulted in heads. Calculate tails as total flips minus heads. Calculate updated SA parameter for the posterior from prior and data. Calculate updated BA parameter for the posterior from prior and data. Create an array of 101 values evenly spaced between 0 and 1 for plotting. Create a new figure for the plot with a width of 6 and height of 2 inches. Plot the posterior distribution's probability density function over X grid values. Label the X-axis as a probability of heads. Set the plot title to show number of flips and true coin probability. Display a legend to identify lines on the plot. Show the completed plot to the user. Running the cell now. This plot shows the updated posterior distribution for the coin's probability of heads after flipping it n times, combining your prior beliefs, prior_A, prior_B, with observed data, number of heads and tails. Notice how changing the prior or sample size shifts the shape and concentration of the posterior, illustrating how Bayesian updating balances prior knowledge with new evidence. This visualization helps you see how your confidence in the coin's bias evolves as you gather more flips. Practice, repeat several times to see how Bayesian updates behave. Try with few flips, strong priors, and biased coins. Before you go, support this channel if you found value. This is a comment asking viewers to like and subscribe. This line prints a message encouraging viewers to like and subscribe for more lessons. Running the cell now. This output shows a simple print statement designed to engage the audience, not statistical data. It reminds us that beyond Bayesian concepts, clear communication and calls to action are important in teaching data science effectively. Here, the focus is on encouraging viewers to support the lesson, reinforcing the intent to build a learning community. Share this video with a friend who wants to learn practical statistics.